Welcome. Today we are diving deep into one of the most incredible pieces of engineering in the entire universe, the human ear. It's a fascinating journey, and I'm excited to guide you through it.
So, have you ever really stopped to think about it? How does a simple pressure wave moving through the air transform into something as profound as music or a conversation with a friend? It honestly seems like magic, but it's pure, elegant physics and anatomy. And today, we're going to pull back that curtain and see exactly how it all works.
To get our bearings, we need a map. Our tour today is broken down into three main sections, and we're going to follow the exact path that a sound wave takes. We'll start on the outside with the external ear, then move into the really clever mechanical world of the middle ear, and we'll finish up in the inner ear, which is where the real magic of hearing actually happens. All right, so let's kick things off with the only part of the ear we can actually see. Its job is pretty simple, but it is absolutely crucial. It's designed to act like a funnel, gathering all those sound waves from the world around us and pointing them inward.
This part here is called the auricle, or pinna, and it's not just there to hang your earrings on. Its unique, swirly shape is perfectly designed to capture sound. Now here's a cool detail. See that small notch right there? It's called the incisura terminalis. And for surgeons, this little cartilage-free spot is a super important landmark. It gives them a natural, safe pathway to get inside the ear canal. Pretty neat, right?
So, once the auricle has collected the sound, those waves travel down this tunnel, the external auditory canal. It's about 24 millimeters long, and its whole job is to guide those vibrations straight toward the eardrum.
But, this tunnel isn't the same all the way through. The outer third is made of cartilage, and it's lined with skin that has hair and special glands that make earwax. Now, this part also has these tiny passages called the fissures of Santorini, and you want to pay attention to these because they can sometimes be a pathway for infections to travel from the outside into deeper tissues. The inner two-thirds, on the other hand, is bony, and the skin there is super thin, super sensitive, with no hair or wax glands at all.
Now, right before you get to the eardrum, the canal hits its narrowest point. This spot is called the isthmus, and this little anatomical bottleneck, well, that's the exact reason why foreign objects, like a kid sticking a bead in their ear or the tip of a cotton swab, get stuck right there so often. Okay, for our next stop, I want you to just look at this number, 0.1 millimeters. That is incredibly thin. We're talking about the thickness of a single sheet of paper. So what on earth inside the ear could be that delicate, but also powerful enough to do its job?
Well, it's the tympanic membrane. You probably know it as the eardrum. This amazingly thin structure is the barrier between the external ear and the middle ear. Most of it is a tight, vibrating surface called the pars tensa, and then there's a smaller, looser section up top called the pars flaccida. And think of it like a perfect little three-layered sandwich. You've got skin on the outside, a mucosa lining on the inside, and a super important fibrous layer in the middle that gives it the strength to vibrate like crazy without ever tearing.
So, once a sound wave hits that delicate eardrum and makes it vibrate, we've officially passed into the second region of our tour, the middle ear. And I want you to think of this space less like a passageway and more like a sophisticated mechanical amplifier. Its whole job is to convert those weak airborne vibrations into powerful mechanical energy.
The best way to really wrap your head around this space is to picture it as a tiny, six-sided box. It's packed with crucial machinery, and it's surrounded on all sides by some really important structures. Each wall of this box is right up against something vital.
And this chart really shows you just how critical this location is. The roof of this little box separates the ear directly from the brain. The floor sits right on top of the jugular bulb, a major vein. The front wall is right next to the carotid artery. And the wall on the inside is the gateway to the inner ear. It really highlights why a middle ear infection can get so serious, so fast. It's a pretty high-stakes neighborhood in there.
So what's inside this box? The three smallest bones in your entire body, the ossicles. And they work together like a beautiful little set of levers. The eardrum vibrates and moves the malleus. That's the hammer. The hammer moves the incus, or the anvil. And the anvil pivots the stapes, the stirrup, which then pushes its little footplate into a tiny membrane called the oval window. And just like that, the vibration is passed into the inner ear.
And that push brings us to our final destination, the inner ear, also known as the labyrinth. We have collected the sound, we have amplified it, and now we've arrived at the place where all that mechanical vibration finally gets translated into the electrical language that the brain can understand. This is where hearing truly happens.
Okay, to understand how the inner ear works, you first have to understand its two crucial fluids. The outer bony part is filled with something called perilymph, which is really rich in sodium. But nestled inside of that is a soft, membranous labyrinth that's filled with endolymph, which is rich in potassium. And that chemical difference between the two, that's literally the battery that powers our entire sense of hearing.
And now for the star of the show, this incredible snail-shaped structure right here called the cochlea. This is the organ of hearing itself. All that mechanical force from the stapes pushing on the oval window creates a pressure wave in the fluid that fills this amazing coiled tube.
So if we could magically unroll the cochlea, we'd see it's divided into 3 fluid-filled chambers. The pressure wave from the stapes travels up one chamber, the skull of vestibule, goes all the way around the tip, and then travels back down the other, the skull of tympani. But the most important part is what's happening in the chamber that's sandwiched right between them, the scala media. As that fluid wave passes by, it causes a membrane in there to ripple, and riding on top of that membrane are thousands of microscopic hair cells. When those little hairs bend, it opens up tiny channels, allowing potassium ions from the endolymph to rush in. And that rush of ions, that creates an electrical spark. That's the nerve signal. That is the sound.
Wow. Okay, so we've seen all the individual parts up close. Now let's pull the camera all the way back and put it all together to see the complete, incredible journey that a single sound wave takes from the air all the way to your brain.
Here we go. First, the auricle collects the sound. The canal funnels it to the eardrum. The eardrum vibrates, which sets the ossicles in motion. The stapes pushes on the oval window, creating a pressure wave in the cochleus fluid. That fluid wave travels through the chambers, stimulating those amazing little hair cells, which, finally, convert all that motion into an electrical nerve signal that gets sent right to the brain.
I mean, when you really trace that path from start to finish, you realize it is just astonishing. The entire system, from that outer funnel all the way to the inner labyrinth, is truly a masterpiece of biological engineering.
And what's really incredible is that this whole complex, multi-stage process happens so fast and so flawlessly that we just perceive it as sound. It really makes you wonder, doesn't it? What other hidden marvels of engineering are quietly at work inside of us, right at this very moment? Thanks so much for joining me on this tour.